welcome to our lectures on fax devices. Today we will continue with the GCSC from where we left in previous lecture. So, let us recall our previous discussion. There actually the TCR, that is the thyristor controlled reactor, is controlled by the turn on delay. So, please please recall your TCR in your shunt compensation with respect to the crest of the applied voltage, that is at the peak of the applied voltage, which defines the conduction interval of this thyristors or GTO, or that can be actually termed as valve, because it can be a combination of the series and parallel combination to meet that voltage and current requirement. The GCSC is controlled by turn off delay. So, this is one of the basic difference. So, for this reason we require GTO, not the thyristor, with respect to the peak of the line current. So, it will be actually it will be measured from this actually turn off time, and which basically defines the blocking interval of the valve. And what are the other difference, though it seems look similar? This TCR controls the current in a fixed inductor from a constant voltage source. This is the TCR, and representing a variable reactive admittance as well as the load and the source. On the other hand, GCSC controls the voltage developed by a constant current source across a fixed capacitor, and thus thereby representing the variable impedance source. So, this is the basic difference of TCR and GCSC. So, similarly, please recall our expressions in current. So, you had a same kind of term, that is IFL equal to I0 by 1 minus lambda by pi 1 by same term will be there. So, then here it will be the voltage. So, it is I by omega c, that is a impedance of the line. By using the duality of the amplitude of C lambda, the fundamental capacitor voltage CF can be expressed as a function of the angle lambda. So, there you used to write alpha, here you will write lambda. So, CF lambda equal to 1 by omega c, 1 minus 2 by pi into lambda by 1 by pi sin 2 lambda. Again this equation has to actually, you require to solve this equation. This is a nonlinear equation, and you have to solve this equation by the iterative method, where definitely it is a trivial statement where I is the amplitude of the, let me change the color of the ink to red. So, amplitude of the line current, and C is the capacitor of the capacitor that connected across to the GTO, and moreover varying the fundamental capacitor voltage at a fixed current could be considered as a variable capacitive impedance. So, we should have a variable capacitive impedance, and thus we can rewrite this equation of the variable impedance as Xc, that is function of the lambda is 1 by omega c 1 minus 2 by pi lambda minus 1 by pi sin lambda. So, let us see the contour and the VI characteristics of GCSC. In a practical application, the GCSC can be operated either to the compensating voltage Vc or the compensating reactance. So, we can have both the operation, and we can choose one of the operation. In case of the voltage compensation mode, that means this mode, GCSC has to maintain the rated voltage in phase of the decreasing the line current over the definite interval of time. So, it is changing. So, we have to maintain the desired voltage level. So, it is I mean should be so actually you have to control this I within this range. In the capacitive reactance range Xc, it is selected so as to produce the rated compensated voltage. So, that should be I equal to I mean, that means Vc max equal to Xc into I mean. So, this is the operation, this is the Vc max, this is the I mean and this is I max. You can control in this region, this is a constant impedance mode. You can control in this mode, this is something like you recall that in DC motor there is a constant torque region and constant power region, it is something like equivalent to that. So, here actually it is operated in constant voltage mode. So, here voltage remain constant and here the slope remain constant and thus impedance remains constant. As the current I mean is increased towards I max, then the turnover angle delay lambda is decreased to reduce the duration of the conduction. Now, what is the loss? The loss as percentage of the rated VAR output versus current characteristics of the GCSC operated in the voltage compensation mode is shown here. So, what happened in GCSC to maintain the maximum rated compensated reactance at any line current up to the maximum up to the current up to the rated maximum. So, in this compensation mode the capacitive impedance is chosen so as to provide maximum series capacitance compensation. So, that will be actually Vc max equal to Ic into I max. So, this is actually the Vc max value and ultimately this is the constant impedance shown and this is a constant voltage shown. So, loss versus line current characteristics of the GCSC for the impedance mode, it is been shown here. So, this is x axis is I and y axis is basically the losses. For 0 impedance, for 0 compensating impedance, capacitor is bypassed. So, you got a very low losses basically. The capacitor is bypassed by the GTO valve. For the maximum compensating impedance, the GTO valve is open and capacitor is fully inserted. The impedance and the voltage compensating modes are of course interchangeable in control action. So, this is the operation of the GCSC and we can see that with increase of the current, since there is a actually there is a fixed drop fixed conduction drop across the GTO. So, for this reason what happened? So, conduction drop will increase linearly with the conduction time and thus increasing I generally this losses increases. Now, to the turn off delay angle control of GCSC is just like same of the turn on delay control of the TCR and it generate the same thing harmonics. For identical positive and the negative voltage half cycle, this odd harmonics is generated, it is something like this. We have assume that the odd symmetry and this kind of harmonic content will be generated. So, Vc and lambda is given by 1 by omega c 4 by pi is a fundamental. So, thereafter you have other harmonic and generally the harmonic content will be fast, third and so on, that is the content is actually n k plus 1. So, you have a actually this kind of harmonics. So, we require to eliminate that harmonic, that is also an important thing. So, we had eliminated the harmonic by different kind of delta connection in case of the TCR, same principle can be used here. So, to elimination of the triplet and other harmonic, families in the capacitor voltage by usual method of the 3-phase operation, and multiple circuit structures are probably not practical in case of the GCSC, because you require to insert a transformer, delta transformer, because those approaches would usually require insertion of a transformer. So, how can we get rid of those harmonics then? So, this is basically the harmonic spectrum of the GCSC. This is the fundamental will decay as the triggering angle changes, and you can see that actually around 37 degree you will have a peak of the third harmonic, and accordingly different values you have a different content of the harmonic. The amplitude variation of the harmonic is expressed as a percentage of the maximum fundamental of the capacitor voltage. So, this is almost same as TCR. So, what should we do then to get rid of this dominating harmonic? You can see that, if you see that, observe this previous slide, that third harmonic content is much more than the fundamental when its peaks occurs. So, we require to reduce the third harmonic. The effect of this harmonic may be relatively small except the third harmonic definitely, particularly if the transmission line impedance frequencies is considered to be relatively large. If necessary, the magnitude of the harmonics generated by GCSC can be attenuated effectively by the complementary application method of the sequential control. What is sequential control? We should actually have a pulse, we should have a actually common mode choke or those kind of thing that will basically cancel out the positive and the negative fluxes. Since recall that 5th and 7th are the positive and the negative sequence. So, it follows from the duality that TCR that requires to use of M where M is greater than 2, the series connected GSC each with 1 by M total such rating is required. So, you have to put them in series. So, M minus 1 capacitor sequentially controlled by inserted valve is on or off or bypass mode. The single capacitor turn off delay angle control to facilitate the continuous voltage control of whole GCSC over a operating range. This is the advantage of it. With this arrangement, the amplitude of the each generated harmonics is eventually reduced by the factor of m in the relation of the maximum total fundamental component of the voltage. So, you can increase the number of valve and thus you can eliminate or you can reduce the content by 1 by m times. So, see that this is the way of operation. So, total voltage it is Vc1, Vc2, Vc3, Vc4 and these are the anti-parallel GTOs are connected. So, this is the VCC. In first cycle all were switched on. So, the current will be actually flowing like this. Thereafter Vc2 is turned off after third cycle and thereafter Vc3 is turned off here after fourth cycle and Vc4 will be actually will have this kind of alpha control sequence and thus overall voltage and current will have this kind of nature. In that way you can actually eliminate also the harmonics. So, the loss of the sequential controlled GCSC are inversely proportional to the VAR output. Since it is dependent on the current rating, it is a current control device. So, it is I square x GC, the loss of the maximum that means about 70% of the rated valve voltage when all the capacitor of the sequentially controlled GCSCs are bypassed and thyristor is and this actually the GTOs are fully on. They are negligible when all the capacitor are fully inserted, when all the actually GTOs are off. So what we can do then? Why not replace the GTO valve in M-1 module with a less expensive thyristor module, because it is a current control device. Since you are turning off the GTO of the thyristor in series, in GTO in series. So, no current will flow through the thyristor and thyristor will automatically go off. So, less expensive conventional thyristor module, because the conventional thyristor valves operations of the total valve will be would be different, or the conventional thyristor valve cannot imitate the GTO valve operation even full condition of the capacitor switching. In order to obtain the half cycle wave, the GTO valve must turn on and turn off when capacitor voltage is 0, at which instant the line current is at the peak. So, this is something we require to do it. So, turn off control is required. So, it is only possible with the GTO. Thus, the conventional thyristor valve could be turned off at the required instant when voltage is 0, but it will only off at the current 0. So, that is something we require to keep in mind. So, it is not possible to replace always the GTO this GTO by thyristors. And thus, when this conventional thyristor valve turns off at 0 current, it produces the full DC offset voltage to the capacitor, and thus it doubling the capacitor voltage across the thyristor. So, it is doubling the maximum voltage. So, what will happen then? The stress on the valve and the time delay after which the capacitor again will be bypassed will increase. So, we cannot actually replace this GTO by a thyristor. Now, these are the discussion about the GCSC. Now, let us now go to the discussion on the another static device of series type called static synchronous series compensator. So, it is equivalent almost to the STATCOM, and but it has a series compensation. So, it is triple SC. So, what does it do? It has been established that voltage source converter with internal control can be considered as a synchronous voltage source, and it is analogous to the ideal electromagnetic generator without any rotating part, thus does not have any inertia. It can produce a set of 3 alternating subsequently sinusoidal voltages at the desired fundamental frequency with controlled amplitude and the phase angle generation, and or absorb the real or reactive power. Generally, it is made for absorption of the reactive power. Real power is automatically consumed to meet the losses. It can also exchange real power with the AC system when its DC terminals are connected to the suitable electric DC energy source storage cell. Now, this is the configuration. So, ultimately you got a coupling transformer. This is analogous to the STATCOM solution in the shunt, but it is series. So, this is a voltage source converter. According to the switch, it will generate the reactive power, and if it is just comes with the capacitor to meet the losses and the harmonics, then it can inject the voltage and compensate the reactive power. Otherwise, if you have a storage device, so it can also inject the real power. So, the reference Q ref and the P ref define the amplitude V and phase angle sigma is generated, phase angle psi is generated output voltage necessary to exchange the desired reactive and the active power AC output. So, if SVC operated, SVS operated strictly for the reactive power exchange by setting P ref equal to 0, that means you do not require any storage element. So, you have a V equal to V sin omega t minus phi, and you have a coupling transformer. So, that will step down to the desired level, so that the semiconductor switches can operate. Semiconductor switch will generate the voltage and current in a desired phase shift as determined by the P ref and the Q ref, and this voltage will be injected in series. So, this is the principal operation of this device SSSC. So, what does it do, you know? The voltage source converter based series compensator is called static synchronous series compensator, or in abbreviation SSSC. The basic operation principle can be explained with a reference of the conventional series compensator with the related voltage phasor diagram. So, this is the this is the VC, and this is the inserted impedance, and this is XL, and you know that in series compensation that P become V square XL minus XC into sin delta. The phasor, and ultimately this one is VL and this one is VC. So, ultimately this difference is VL and VC. The phasor diagram clearly shows that at a given line current, the voltage across a series capacitor forces the opposite polarity voltage across the series line reactance to increase the magnitude of the capacitor voltage. While it may be convenient to consider a series capacitor compensation as a means of reducing the line impedance, in reality, as I explained previously, it is really a means to increasing the voltage across the given impedance of the physical line. So, here this will act as a source and that will add up with it, and that voltage source of course is going to be in quadrature with phase, since it is a capacitor. So, therefore, that same steady state power transmission can be established if the series compensation is provided by a synchronous AC voltage source. That is the basic principle of operation of the SSSC, whose output precisely matches with the voltage of the series capacitor. Thus, VQ equal to VC equal to minus J IXC equal to minus J K into IXC, where K is the ratio of XC by X or XL, where VC is the injected compensating voltage phasor, I is the line current, X is the reactance of the series capacitor, X is the line reactance, and K is XC by X is the degree of the series compensation, and thus making the output voltage of the synchronous voltage source a function of the line current, the same compensation as provided by the series capacitor can be accomplished. Well, what is the difference? Difference is, contrast to the real series capacitor, it is able to maintain a constant compensating voltage VQ. That is the previously we were compensating the impedance, then you are injecting a voltage in presence of the variable line current. That is the difference. So, or control the amplitude of the injected compensating voltage, the impedance of the amplitude of the line current. So, what happened then? For this reason, for normal capacitive compensation, the output voltage lags the line current by 90 degree, and it can be achieved by the output voltage that reverses the control action. So, we see this in next slide. So, in this case the injected voltage decreases the voltage across the inductive line impedance, and thus the series compensation has the same effect as of the reactive line impedance was increased. So, this is the principle of operation. With the above observation, generalized expressions for the injected voltage V q can be written that plus minus V q function of the V and by I by I m the unit vector, where V q is the magnitude of the injecting compensating voltage and within a range of 0 to plus V q max. So, V is chosen as a control parameter. So, we can we are about to actually in the last part of our class we will continue with the SSSC in next class. Considering the sending end voltage V lambda and the receiving end voltage V 0, so we can rewrite this equation. So, it is x equivalent, we can write x equivalent, and thus we can write the sending end power. So, the power sent by the line is V square by x 1 minus V q by I sin delta, and thus we can model it as a voltage source which is perpendicular or in quadrature with the V s, and this is the power P q equal to V square x L minus P q by I sin delta, and this is the phasor where mod V s equal to V r equal to V. So, this is the delta and this is V L and this is the V q, ultimately this becomes your actual voltage and it is the perpendicular to this line I s. So, this is the case of the voltage injection. Now, the SSC injects a compensation voltage in series with the line irrespective of the line current. The transmitted power P q versus the transmitted angle delta relationship is therefore becomes a parametric functions of the injected voltage V q. So, it will depend on the V q and it can be expressed for the two machine model. This part is same as the uncompensated line. Thereafter, this value will come V by x V q, but V q can be, it may vary to 0 to 0.5 per unit. So, accordingly this power sent by this limit will change and this is the V q cos delta. So, what is the comparison? Comparison is series capacitor increases the transmitted power by a fixed percentage of the transmitted power by uncompensated line at given delta, and SSC SSSC can increase by a fixed fraction of the maximum power by transmitted power of the uncompensated line by independent delta, because this term does not change by delta. We shall continue with the TCSC discussion in our next class, and then we shall discuss its characteristics over the GCSC, and thank you for your attention.